Welcome to ReneEnergy.com, your renewable energy and sustainability platform. Welcome to the ReneEnergy.com YouTube channel. In today's feature, we delve into the groundbreaking integration of digital twins with green hydrogen production. This fusion of advanced digital technology and sustainable energy practices is not just a glimpse into the future of energy, it's happening now, and it's transforming the way we think about and produce green hydrogen. Join us as we explore this exciting development in detail. Section 1. The role of digital twins in green hydrogen production. 1. Introduction to digital twins. The concept of a digital twin is not new in the world of technology, but its application in green hydrogen production is a relatively recent development. A digital twin is a virtual model of a physical process, product, or service. This pairing of the virtual and physical worlds allows for data analysis and system monitoring to prevent problems before they occur, prevent downtime, develop new opportunities, and even plan for the future by using simulations. 2. Green hydrogen production. Before diving into the role of digital twins, let's understand green hydrogen production. Green hydrogen is produced using renewable energy sources, primarily through the process of electrolysis. This process involves using electricity, preferably sourced from renewables like solar or wind power, to split water into hydrogen and oxygen. The key here is that the electricity used comes from renewable sources, making the hydrogen production truly green and sustainable. 3. Electrolysis and digital twins. The electrolysis process, while efficient, can be further enhanced with the use of digital twins. By creating a virtual replica of the electrolysis process, engineers and scientists can monitor and tweak the process in real time, ensuring maximum efficiency and minimal waste. The digital twin allows for a detailed analysis of the process, identifying areas where energy use can be reduced, where components may fail, and where operational efficiencies can be improved. 4. Optimizing green hydrogen production. The ultimate goal of using digital twins in green hydrogen production is to optimize the process, making it as efficient and cost-effective as possible. By having a detailed virtual model, it's possible to run simulations to determine the best operational conditions. This means adjusting variables like temperature, pressure, and electrical current to see how they impact efficiency and output. The digital twin becomes an invaluable tool for continuous improvement, allowing for tweaks and adjustments that can significantly impact the overall efficiency of the hydrogen production process. 5. Predictive maintenance and safety. Another critical aspect where digital twins contribute is in predictive maintenance. By monitoring the electrolysis equipment in real time, the digital twin can predict when parts might fail or when maintenance is needed. This proactive approach not only reduces downtime but also significantly enhances safety. 6. In an industry where the handling of hydrogen, a highly flammable substance, is a daily occurrence, ensuring equipment is functioning correctly and safely is paramount. 7. Environmental impact and sustainability. Digital twins also play a vital role in assessing and minimizing the environmental impact of green hydrogen production. By accurately modeling the production process, digital twins can identify areas where energy use can be reduced, thus lowering the overall carbon footprint of the process. Additionally, they can help in optimizing the use of renewable energy sources, ensuring that the green hydrogen production process is as sustainable as possible. 8. Integration with renewable energy sources. A unique challenge in green hydrogen production is the integration with variable renewable energy sources like wind and solar power. Digital twins can help in this integration by simulating various scenarios and energy supply patterns, ensuring that the electrolysis process runs efficiently even with the intermittent nature of renewable energy sources. This integration is crucial in truly realizing the potential of green hydrogen as a sustainable energy source. 9. Challenges and future directions. While the use of digital twins in green hydrogen production is promising, it's not without challenges. One of the primary challenges is the need for high-quality, real-time data to feed into the digital twin for it to be effective. Additionally, as this technology is relatively new in the field of green hydrogen, there is a learning curve involved in its implementation. However, the future looks bright. As technology advances, and as we gather more data and insights, the effectiveness and efficiency of digital twins in green hydrogen production will only improve, paving the way for a more sustainable energy future. Section 2. Benefits and applications of digital twins in green hydrogen. Introduction to benefits. The application of digital twins in green hydrogen production offers a multitude of benefits. These benefits not only enhance the efficiency and effectiveness of hydrogen production but also contribute to the overall sustainability of this energy source. Cost reduction and efficiency. One of the most significant benefits of digital twins in green hydrogen production is the potential for cost reduction. By providing a real-time, comprehensive view of the electrolysis process, digital twins enable operators to identify inefficiencies in areas where resources are being wasted. This can lead to substantial cost savings over time. Additionally, the efficiency of the production process is significantly improved. By simulating different scenarios, digital twins allow for the fine-tuning of processes, ensuring that the most efficient methods are used. Predictive maintenance. As mentioned earlier, digital twins play a crucial role in predictive maintenance. By anticipating equipment failures and maintenance needs, digital twins can help avoid costly downtime and extend the lifespan of the equipment. This not only saves money in terms of repairs and maintenance but also ensures that the production process is not interrupted, leading to more stable and reliable hydrogen production. Optimizing operational parameters. Digital twins allow for the optimization of various operational parameters in the electrolysis process. This includes adjusting factors such as temperature, pressure, and the composition of the electrolyte. By simulating how changes to these parameters affect the efficiency and output of hydrogen, operators can find the optimal conditions for production, thereby maximizing output and reducing waste. 2. Enhancing safety and compliance. Safety is a paramount concern in hydrogen production due to the volatile nature of hydrogen. Digital twins contribute to enhanced safety by providing detailed insights into the operational status of the production equipment, allowing for immediate action if any safety risks are identified. Moreover, digital twins can help in ensuring compliance with environmental and safety regulations by providing accurate and real-time data on various aspects of the production process. 3. Environmental monitoring and sustainability. Digital twins serve as a powerful tool for environmental monitoring. By simulating the entire production process, they can predict and analyze the environmental impact of different operational scenarios. This enables the identification of strategies to minimize energy consumption and waste, thereby enhancing the overall sustainability of green hydrogen production. Integration with renewable energy. A critical challenge in green hydrogen production is effectively integrating with intermittent renewable energy sources like solar and wind. Digital twins help in this regard by simulating energy availability and demand scenarios, allowing for a more seamless integration. This ensures that the hydrogen production process is as green as possible, using the maximum available renewable energy. 5. Data-driven decision-making. In the era of big data, digital twins stand out as a key enabler of data-driven decision-making in green hydrogen production. They provide a wealth of data that can be used to make informed decisions about various aspects of the production process, from operational tweaks to long-term strategic planning. 6. Customization and scalability. Digital twins offer a level of customization that is crucial for the diverse needs of different hydrogen production facilities. They can be tailored to the specific needs and circumstances of each facility, ensuring that the solutions they provide are as effective as possible. Additionally, digital twins are scalable, meaning they can be used in small pilot projects as well as large-scale commercial operations. Challenges and opportunities for improvement. While the benefits of digital twins in green hydrogen production are substantial, there are challenges to be addressed. These include the need for continuous data input, high initial setup costs, and the requirement for specialized skills to operate and interpret the data provided by digital twins. However, these challenges also present opportunities for improvement and innovation in the field. Section 3. Recent developments in digital twin technology and future outlook in green hydrogen. Innovations in digital twin technology. The field of digital twin technology is rapidly evolving, with continuous innovations enhancing its application in green hydrogen production. One of the most notable recent developments is the creation of more sophisticated and integrated digital twin models. These models are not only more accurate in replicating the physical processes of hydrogen production but also more adept at simulating complex interactions between various components of the production system. Case studies and real-world applications. There have been several successful implementations of digital twin technology in the green hydrogen sector. For instance, some hydrogen production facilities have adopted digital twins to optimize their operations, leading to significant improvements in efficiency and reductions in operational costs. These real-world applications provide valuable insights and serve as a blueprint for other facilities looking to integrate digital twins into their operations. Collaborative efforts and research initiatives. The advancement of digital twin technology in green hydrogen production has been bolstered by collaborative efforts between research institutions, technology companies, and energy producers. For example, research teams at leading universities and technological institutes are working on developing more advanced digital twin models specifically tailored for green hydrogen applications. These collaborations are crucial in driving forward the technology and its practical applications. Integration with IoT and advanced analytics. A key trend in the development of digital twins is their integration with the Internet of Things, IoT, and advanced analytics. By connecting digital twins with a network of sensors and devices, real-time data can be fed into the models, enhancing their accuracy and responsiveness. Advanced analytics, including machine learning algorithms, are being used to process this data, providing deeper insights and more accurate predictions about the hydrogen production process. Challenges in implementation and adoption. Despite these advancements, there are challenges in the wider implementation and adoption of digital twin technology in the green hydrogen sector. One of the main challenges is the need for substantial investment in technology and infrastructure. Additionally, there is a skills gap, as operating and interpreting digital twins require specialized knowledge and expertise. Future outlook and potential impact. Looking ahead, the potential of digital twin technology in green hydrogen production is immense. As the technology continues to mature and become more accessible, it's expected to play a pivotal role in optimizing production processes, enhancing efficiency, and reducing environmental impact. The future may see digital twins becoming a standard component in the design and operation of green hydrogen facilities. Expanding scope and capabilities. The scope of digital twins is expected to expand beyond just operational optimization. Future developments could include enhanced capabilities for long-term strategic planning, integration with global energy grids, and even assisting in the design of new, more efficient hydrogen production technologies. As the digital and physical worlds continue to converge, the possibilities for innovation and improvement in green hydrogen production are virtually limitless. Promoting sustainability and energy transition. One of the most exciting aspects of the future of digital twins in green hydrogen production is their potential to significantly contribute to sustainability and the global energy transition. By making green hydrogen production more efficient and cost-effective, digital twins can help accelerate the shift away from fossil fuels and towards renewable energy sources. This aligns with global efforts to combat climate change and promote sustainable development. Industry and government collaboration. The successful integration of digital twin technology and green hydrogen production will likely require increased collaboration between industry players and governments. This could involve joint investment in research and development, sharing of best practices, and the creation of policies and frameworks that support the adoption of digital twin technology. Such collaboration will be key in overcoming the challenges and realizing the full potential of this technology. Conclusion. As we wrap up our exploration of digital twins in the green hydrogen industry, it's clear that we are standing at the precipice of a major technological revolution. The convergence of digital twin technology with sustainable energy practices, particularly in green hydrogen production, offers a glimpse into a future where energy efficiency, cost-effectiveness, and environmental responsibility go hand in hand. Digital twins represent more than just a technological innovation. They symbolize a new era in energy production where data, analysis, and virtual modeling drive real-world decisions and outcomes. The potential benefits, from operational efficiency and cost reduction to enhanced safety and environmental sustainability, underscore the transformative impact this technology could have on the green hydrogen sector and the broader energy landscape. However, the journey doesn't end here. The continuous evolution of digital twins and their integration into green hydrogen production presents ongoing opportunities for learning, innovation, and improvement. As technology advances, so does our ability to harness it for a more sustainable future. We invite you to join this exciting journey. Stay informed about the latest developments in digital twin technology and green hydrogen by subscribing to the reshaping.com YouTube channel. Share this video with your network to spread awareness about this groundbreaking technology and its potential impact on our energy future. Your engagement and curiosity are what drive us to uncover and present the most cutting-edge topics in sustainable energy. Together, we can contribute to a more sustainable, efficient, and green future. Remember, the future of energy is not just something we inherit, it's something we create. Thank you for being a part of this journey with ReneEnergy.com. Thank you for choosing ReneEnergy.com as your go-to source for all things renewable energy and sustainability.